morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are talking about the Poisson Distribution. I don't know how to pronounce it. We are being ushered in by my latest obsession as far as music is, Prayer in C. It's a semi-obsession. I'm not sure, and it's a remix and the whole deal, but I kind of like it. Anyway, you're bored already. Let's move on, shall we? Okay, so what is this Poisson? It was introduced by the French mathematician Simeon Denis Poisson. And all it is, it's the binomial distribution where the number of trials goes to infinity. In the binomial distribution, we knew the number of trials, but here we're going to have an infinite number of trials. And remember, the binomial distribution was the probability of obtaining a certain number of successes in a given number of independent trials. Poisson is used to determine the probability of obtaining a certain number of successes within a certain interval of time or space. Like, here's some nice examples: number of incoming telephone calls per hour, misprints on a typical page of a book, number of fish caught in a large lake per day, that's a time period, and so on. And so, this is it. This is the Poisson. The probability distribution for the discrete Poisson random variable is the probability of the specific value x is equal to the probability of the random variable x equal to that specific value, m to the x e to the negative m over x factorial. X is equal to non-negative integer, and m is the parameter of the distribution. We are going to be using the mean, okay? And there's a nice proof on Khan Academy. This first one is the start of the proof, and it goes into another video. And about the first half of it gives a little bit of a more detailed and real-world explanation. If you want to take a look at it, I watched it and enjoyed it. So I just wanted to show that to you. Okay, so what are we doing? All right, so under door number 1, we have this. If the random variable x is a Poisson discrete random variable with a parameter mu, then mu equals m, and the variance is equal to m. We can describe a Poisson distribution using the single parameter m, which is nice. And this is how we write it. If the random variable x is a Poisson random variable, then we write x is distributed as the Poisson of the mean m. And here's how it appears on your formula sheet. One more thing before we show a couple of examples. Here are the conditions. We have to assume that the conditions or the probabilities won't change from hour to hour. Khan gives the example of number of cars passing, an intersection or going through an intersection within an hour. We assume that's not going to change for hour to hour, the number. We know that's not true, but we make that assumption. And then the probability of more than one occurrence in a given interval is very small, and the number of occurrences in disjoint intervals are independent of each other. So if there's 3 million cars that pass during hour 1, that doesn't affect the number that pass through the intersection in hour number 2. So let's just kind of walk through something here. Let's say our friend Sandra, she proofread 80 pages of text of a textbook. That we make the assumption that it's not the whole textbook. It really doesn't matter, actually. She observed the following distribution for the random variable x, the number of errors per page. So 0 errors happened 3 times, 1 error happened 11 times, and this is per page. On down the line, 5 errors on a page happened 9 times. Okay, easy peasy calculating the mean of all this data, 3.2125, and using the Poisson model, which is this guy here, right here for a particular value. So using this formula, we came up with these frequencies. Okay. Now, this is for the Poisson model is for a specific instance. So if we're doing frequencies here, once we get that value, we have to multiply it by the number of trials or number of pages or whatever, which would be 80. Okay, so we get 3.22, and these are probabilities, 10.3, 16.6, and so on. Okay, and that is fairly close to the actual values. So using Poisson, oh, these aren't probabilities, sorry, these are the probabilities that, the number that come from using Poisson to predict the probability. And you can see that using Poisson, it gives a pretty good, pretty close to the actual values that are actually there, given just a little bit of data. Okay, and so then we can see this through for the rest of the book. Also, we get the variance for this approximately equal to 3.367, which is close to m of 3.2125. So let's do one example here, and then I will leave you alone. Okay. So A, find the mean of the distribution. What are we doing here? Sorry. 1 gram of radioactive substance is positioned so that each emission of an alpha particle will flash on a screen. The emissions over 500 periods, so there is our number of trials of 10 seconds duration, are summarized in the following table. So number of flashes of 10 seconds, 0 times happen 90, number of flashes happen of 0 equals happen 91 times. Sorry for stammering. 2 per period happened 132 times, and so on. So to find the mean of the distribution, hopefully we know how to do that. I'm not even going to write 0 times 91, so that would be 1 times 156 plus 2 times 132 plus, oops, sorry, pen's acting a little wacky. I can't get rid of that. Okay, I'm going to have to use the mouse. So let's get rid of that. Okay, so plus dot 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 plus all the way to 7 times 1 divided by the total number here, which is 500, which we already knew, 500 periods, right? 500. Okay, or I'm sorry, the frequency. So that would be equal to 1.694. Okay, and I'm using the mouse, so forgive me while the pen charges. B. Okay, fit the Poisson model to the data and compare the actual data to that from the model. Okay, so this is, we're using this Poisson model to predict future occurrences based on the data that we just had. Okay, definitely having troubles here with my pen. Sorry. Okay, B. Let's see how this goes. Okay, so we're going to use M equal to 1.694. And so then probability that X is equal to X using Poisson would be this right here. So that would be 1.694 to the X, little x, e to the negative 1.694 all over x factorial. Okay, so if I just did, I don't know, let's do probability that, well, we'll start with the first one, x equals 0. It's very simple, very easy. And you can just crank this on your calculator. I'm just showing you step by step here. 1.694 to the 0, e to the negative 1.694, all over 0 factorial. We're just in plug and chug mode here. Okay, and 0 factorial, I hope you know, is equal to 1. And this is approximately equal to 91.9. Okay, so probability that x equals 1 by the same procedure, I will tell you, is 155.7 if you want to try it on your own. Probability that the random variable x equals 2 is approximately equal to 131.8. And blah, 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 all the way to probability that the random variable x equals 7. And that is approximately equal to 0.7. Okay, so I'm not going to do all of them. You get the picture, right? And so the comparison, let's just do a quick comparison. 155.7 to an actual occurrence of 156, pretty close. For 2, 131.8, pretty close. 0.7, you know, pretty close and decent enough to use for an estimation. Okay, so now for part C, finding the standard deviation of the distribution. You know how to do that on your calculator, and I will tell you that it is approximately equal to 1.29. Okay, and the square root of m, which is 1.694, and that is approximately equal to 1.30, right? So these are close. The standard deviation is very close to the square root of the mean, which means the variance is very close to the mean. Okay, so that validates the Poisson as a tool we can use to help us predict. And I think that is all that I have. So let's go back out with this awesome tune. And we will see you next time. I am out.